In the following lecture, we're going to try and do some examples of finding pH of different solutions, and I'm going to briefly give you a brief overview of what we did previously. Previously, I told you that water dissociates or ionizes very, very weakly and produces H+1 and OH-1 ions. And I also told you that if the solution is acidic, or if you have added acid to water, then the concentration of H+1 is going to be higher and the concentration of OH-1 ions would be lesser. Similarly, I also told you that if the solution is or water, if you add a base to water, then the concentration of H+1 ions in water would be lesser and the concentration of OH-1 would be much higher. And so we had this expression of water ionizing, whether the conditions are neutral, acidic or basic, that would vary. And I told you that there was a water constant which was Kw, which was the product of the concentration of H+1 and the concentration of OH-1. And this product would always be a constant. The value of Kw was 1 into 10 to the minus 14 under standard conditions, 25 degrees centigrade and 1 atmosphere pressure. And the value would always be a constant. If it's a neutral solution, then the two ions would have equal concentration. If it's an acidic solution, then H+1 would be higher, vice versa OH-1 would be lower. So the value would still come out to be 1 into 10 to the minus 14. If it's an alkaline solution, then the OH ion concentration would be higher and the H+1 concentration would be lower, but the value would still come out to be equal to 1 into 10 to the minus 14. So we had this expression, and then we took the negative log of that expression, which gave us the negative log of Kw equal to, when you take the log of two things multiplying, after log they're going to be adding up. Since it's a minus log, it's going to be minus log of H+1 minus log of OH-1, that would be equal to minus log of 1 into 10 to the minus 14. This minus log of H+1 was known as pH, and this minus log of OH-1 was known as POH. And this value would come out to be equal to 14. So your final expression that we derived was pH plus POH is going to be equal to 14 under standard conditions. And the reason why we took log in the first place was that the concentration of H+1 could vary drastically. It could be very high or it could be very low. It could be 0.1 mole per decimeter cube, or it could be 0.00001 mole per decimeter cube. So if you want to plot a graph, taking log, what log does is that it expresses everything very large and very small values in the powers of 10, and the values scale up. So it becomes a lot easier to make a graph and plot a graph. So after taking log, so which is why we generally plot, or we generally track the pH of solutions, not the actual concentration of H+1, because it's easier to express. It's going to be in whole numbers, which are much more easier to comprehend. And we also discussed that if pH is lower, that means that the concentration of H+1 is actually higher, and if pH is higher, that means the concentration of H+1 is actually lower, and the same applies for POH as well. Now we're going to try and discuss a few questions. I'm going to do a few questions, and we're going to try and calculate the pH or the POH of different solutions. So here is my first question, which is that I need to find the pH of 0.1 mole per decimeter cube of HCl, and I'm only going to focus on strong acids first. Strong acids fully dissociate or fully ionize. So if I have HCl, and if HCl is aqueous, it's going to completely ionize in water, and it's going to produce H+1 and Cl-1 ions. They would be in aqueous state as well. So complete ionization is going to occur. So if I have 0.1 mole per decimeter cube of HCl, then the amount of H+1 ion, or the concentration of H+1 ion, is going to be exactly the same. It's going to be 0.1 mole per decimeter cube as well. So finding pH becomes very easy for strong acids. If you know the concentration of the acids, you directly know the concentration of H+1 ions in solution. The only thing that you need to do now is simply do the calculation and find the pH. So pH would be equal to minus log of the concentration of each plus 1 ions, and minus log in our case is going to be equal to the concentration of H plus 1 is 0.1 mole per decimeter cube. So if I take the negative log of this using my calculator, I get a value of 1. So my pH for HCl having a concentration of 0.1 mole per decimeter cube, the pH value is going to come out to be equal to 1. Let's try and do the second question. Again, it's a straightforward question. You're supposed to find the pH of a solution that has H plus 1 concentration equal to 2.5 into 10 to the power minus 4 mole per decimeter cube. Always remember that square brackets, wherever square brackets are written, that denotes the or represents the concentration of that substance. So we're talking about the concentration of H plus 1. So I simply need to apply my formula for pH, which is equal to, so pH is going to be equal to minus log of the concentration of H plus 1. So I'm going to take the minus negative log of 2.5 into 10 raised to the power minus 4. And my answer, my value comes out to be equal to 3.6. So the pH is going to be 3.6. And you can also notice that plotting the concentration of H plus 1, 2.5 times 10 to the power minus 4 would be very difficult on a graph paper. But if you take the negative log of this same value, plotting 3.6 on a graph paper is going to be very easy. So this is the importance of taking the negative log. Taking any log of any value would scale up this value. If it's too small or if it's too big, then it's better that you take the log of that value if you're making a graph, because it's going to be very hard to actually plot a billion on a piece of graph paper, or to plot a very small or tiny value like this. You have to then choose your scale very intelligently. So taking log would give you very nice whole numbers, because all the values are converted in the powers of 10. So you're going to get very nice whole numbers, which would be very easy to be. It would become very easy for you to plot those values. So which is why pH is very important instead of H plus 1. Now in this question, I'm going to try and find the pH of an alkali. Now I have KOH, which is a very strong alkali. It fully ionizes. And the concentration of that alkali is 0.02 mole per decimeter cube. So I'm going to write the equation for dissociation of this alkali KOH. If it is aqueous, in aqueous state, it will produce 1 K plus ion in aqueous state and 1 OH ion that would also be in. So OH minus 1 would also be produced. That would also be in aqueous state. So if KOH has a concentration of 0.02 mole per decimeter cube, then according to the ratio, 1 KOH, if 1 KOH dissociates, it produces 1 OH ion. So the ratio is 1:1. So the amount of OH ions in the solution would also be 0.02 mole per decimeter cube. Now, in this question, I have the concentration of OH ions. I don't have the concentration of H plus 1 ions. So I'm going to take that concentration of OH ions and I'm going to instead calculate POH. POH would be the negative log of the concentration of OH ions, which in this case, the concentration of OH ions, the negative log, taking that, it would be negative log of 0.02 mole per decimeter cube. And the answer that I'm going to get is, it is coming out to be 1.7. Now remember, this is your POH. Your POH value comes out to be 1.7. And we had an equation initially that we derived, which was that pH plus POH is always going to be equal to, it's always going to be equal to 14. So using this this expression, if I substitute my POH in this equation, the pH that I'm going to get is going to be, it's going to be pH plus 1.7, that would be equal to 14. And the value of pH would come out to be equal to, it's going to come out to be equal to 12.8. 12.3. So the pH of this alkali would come out to be equal to 12.3, which basically means that I also told you that the higher the value of pH, the lower the concentration of H+1 ions. Using this pH, you can also calculate the concentration of H+1 ions. Our pH comes out to be 12.3 for this KOH, which basically means that if you do the opposite and try and find the concentration of H+1 ions, the value would come out to be equal to 10 to the power minus 12.3 mole per decimeter cube, which is a very, very extremely low value. So the higher the concentration, the higher the pH, the lower would be the concentration of H+1 ions. So if you have an alkali like KOH, the concentration of H+1 ions is going to be very low. The concentration of OH ions, vice versa, would be extremely high. So as you can see, pH comes out to be very high. In reality, the concentration of H+1 is actually very, very low. Let's try and do another example. But this time I'm going to do the opposite now. Now I'm supposed to find the concentration of NaOH, find the NaOH aqueous concentration. And the pH of that solution is given. It's given as 11.8. So I'm going to try and do the reverse now. The pH is already known, and I need to find the concentration of NaOH aqueous. Now, the way I'm going to do that is I have this expression pH plus POH is given as is equal to 14. So I'm going to use this expression, and I'm going to substitute my pH value in this expression. So if I do that, it's going to be 11.8 is equal to is plus POH, that is unknown, equals to 14. And my POH value would then come out to be equal to 14 minus 11.8, which should be equal to 2.2. So I have this POH value now, which is coming out to be 2.2. The reason why I'm interested in the POH value is because NaOH has OH ions, not H+1 ions. So finding the H+1 concentration would be irrelevant because I would not be able to find the concentration of NaOH that way. To find the concentration of NaOH, I need to find the concentration of OH ions in the solution. So which is why I want the POH value, which is coming out to be equal to 2.2. The next step would be that I'm going to do the reverse. I know that POH is basically the negative log of the concentration of OH minus 1 ions. And this is equal to 2.2. So I'm going to take the negative sign first on the right side. So this would become plus, this would become negative. Then I'm going to take the inverse log on both sides. If I take the inverse log on both sides, this would become the concentration of OH minus 1 would be equal to the anti-log of minus 2.2. Or you can press shift log. If you don't know what log is or how the function works, you can press shift and log on your calculator, and you're going to get the answer shift log minus 2.2. But on the other hand, if you know what log is, anti-log of minus 2.2 basically means it's 10 to the power minus 2.2. And this value, this would be equal to the concentration of OH ions, OH minus 1 with square brackets means that you're talking about the concentration of OH minus 1. So let me calculate this on my calculator. And the answer is 0.00064 mole per decimeter cube. So this is the concentration of OH ions, and I can now write the equation of the dissociation of NaOH aqueous. If you have NaOH in aqueous state, then that NaOH is a strong alkali. It's going to fully dissociate, and it's going to produce sodium ions and OH ions in 1:1. So the quantity or the concentration of OH ions and the concentration of NaOH would be exactly the same. If the concentration of OH ions is coming out to be 0.0064 mole per decimeter cube, then the concentration of NaOH would be exactly the same because it's a strong alkali, it fully ionizes. So it's going to be 0.0064 mole per decimeter cube as well. So this is your answer. The concentration of NaOH aqueous would be 0.0064 mole per decimeter cube.